In our ever ongoing quest to solve differential equations, we look for special cases, places where we can actually make progress in solving. We've seen two so far, namely separable differential equations and linear first-order differential equations, whereby we've made progress. Modulo our ability to carry out integration, we can solve. Today we're going to add a third one, and that'll help us solve another case of differential equations called exact ordinary differential equations. So let's get going. So what are exact ordinary differential equations? Well, essentially it's a differential equation that can be written in the following way. Namely, some function m, which depends on x and y, dx, plus some function n, which depends on x and y, dy, equals 0. So we might recall we call this differential form. Now, there's one small extra piece. So we can take any differential equation, oftentimes writing this way, but the small part, the thing that makes it exact, is that we need this extra little twist. Namely, when we take the function m and do this, well, let's talk about that in just a moment, and take the function n and do that, they're the same. Okay, so what are we doing? So let's talk about these things. So when you see this symbol right here, this stands for what we call a partial derivative. And the idea is fairly simple. It's like a derivative, but we're not taking derivative of everything, we're taking derivative of part of something. And in this case, the part here is referring to the variables. So when we look at our functions, there are functions with two inputs. So when we take a derivative, we say, well, wait, derivative of with respect to which are one of the variables. So the question is, which part are we taking the derivative of? So that's why we have this notion of partial derivative. By the way, if you want to know more about partial derivatives, multivariable calculus. You'll love it. Great subject. So our notation here, this stands for derivative. And it's just telling us what kind of derivative. So it's saying take the derivative with respect to y of m. Now when I take the derivative with respect to y, what do I do with the x? And the answer is, treat it like a number. It's a constant. So we're just thinking of only the y part as being varying. And here, we're doing something similar. We're taking the derivative with respect to x of n. And we're saying, all right, great. When we compare these two, if they're the same, partial m partial y and partial n partial x, then it's exact. All right. Well, why do we care? And how does this help us? So it turns out that these exact ordinary differential equations can only come up in a very particular way. In fact, there's only one way that they can be formed. And what it turns out is that there's some function f of xy equals c, where when we take the partial derivative of that function with respect to x, we get m. We take the partial derivative with respect to y, that function we get n. Now, let's take a step back and really say what's going on, because I think it's important to understand why this works and how this ties into our sort of one of our underlying ideas. It's really easy to integrate derivatives. So, here we go. We start with sort of the following notion, namely, suppose we have f of x, y equals some constant c. And so that says there's some relationship between x and y. Because that's what this really says. There's some expression involving x and y. Now, you'll notice there's a word here that I think it's worth to highlight, and that's the word implicit. And when we talk about implicit relationships, that's a type of relationship where we don't really have a good way to isolate a variable. So probably it's easier to say what something is when it's not implicit. So explicit, if we just do a little bit of comparison here, explicit would be something of the form y equals stuff with x, or maybe x equals stuff with y. Those are examples of explicit relationships. Implicit says, well, we don't really have a way to get to that. Now, it's not hard to come up with implicit relationships you could have something like x squared y plus e to the x plus sine of y equals 2. And if we look at this, we say, okay, there's just no way to get x alone or to get y alone. So for instance, you see here there's a y outside, and here there's a y inside. So it's like, well, if I try to free the y here, I trap the y there. And so no matter what, there's sort of a separation going on. So using standard tools, standard trigonometric identities, reduction through algebra, there's no way to get from this kind of thing to y equals stuff with x. So we say this is implicit. Nevertheless, there's still a relationship. It's not that y and x are completely independent from each other. If I tell you something about x, well, that forces something to be true about y. So we say, well, look, even though we can't solve for it explicitly, we know that implicitly that there's this relationship going on. Whoops, I can spell implicitly. We can say, look, y is some function of x. All right, so now let's go back to our story here. Said, suppose we start with this f of xy equals a constant c. That's an implicit relationship. And so, like what we have here, it says, hey, y depends on x in some way that we don't know and understand. But it does. And now we say, oh, let's think about the function f here for a second and ask the question, how does it depend on the variable x? Well, we can say it actually depends on it in two ways, because I can draw f depends on its inputs, which are x and y, because of the relationship, is a function of x. That's what is being said down here. Y is a function of x. And now we say, all right, great. Let's start by taking the derivative of both sides of this expression with respect to x. And let's see what we get. So there's two sides. One of the two sides is very easy, and the other one, we just have to think a little bit. The side that's easy, we'll go ahead and just shout it out first. C. It's a constant. So when we take the derivative of that with respect to 0, we get 0. Now, how do you take the derivative of this function on the left-hand side? Well, this comes back to the idea of implicit differentiation. You'll see this in multivariable calculus, but for right now, we're just going to sort of do some intuitiveness and say what's going on. And what we look for is to say, well, where does x show up? And the answer is it shows up in two places. And so if I want to understand how the variable x influences f, which is what we're after when we talk about taking the derivative of f with respect to x, what we have to understand is how does x affect it in both ways that x shows up. So what we'll have is we'll say, well, one effect is how does a function depend on x directly? And so we'll denote that as partial f partial x. And then there's a separate effect which says, okay, how does f get influenced through x via y? Well, that would be partial f partial y. That's that change. And then dy dx, which is this change here. Now, the astute observer might be saying, wait a second, why are you using partial symbol for derivative here and the d symbol for derivative there? And the reason why is because there's this sort of understanding that we all agree on that says when we have functions of multiple variables, we use the partial symbol, and that's f depends on two inputs. And when we have functions of a single variable, we use the d symbol, which is how we think of as the y function. All right, so these are the two ways that x is affecting the function f. To get the total effect, we add them together. So that's the derivative of the left-hand side with respect to x. That's going to equal the derivative of the right-hand side with respect to x, which is 0. All right, well, now let's just go one small step further and say, change it to our differential convention. And if we do that, we can say, hey, this becomes partial f partial x dx plus partial f partial y dy equals 0. So when I talk about changing to differential, I just say, oh, think of the dy and dx not as a single entity, which is what it's supposed to be, but now as two separate things, and then multiply everything by dx. Now this might look really familiar, like something else that we see on the screen. It's actually this piece right here. So what's happening is we say, aha, when we have an exact ordinary differential equation, it really came from starting with this kind of relationship and taking a derivative. So that's why we like these exact ordinary differential equations. It's coming from a derivative. And if it's something we can solve, well, we know how to solve derivatives, we integrate. So that's why we like exact ordinary differential equations. And it's also the reason why we have a chance. There's a real chance for us to make progress and to solve. So how do we actually do it? Well, so to solve, what do we need to do? We need to find this function capital F of xy. Now this has a name. It probably has several names, but the one that you'll probably see most often is called the potential function. You'll see this in physics. You also see this in multivariable calculus. You might call it the target function. It's the function we're trying to find. And, well, the way to go about it, there's sort of a couple of ways. And I can outline sort of two ways. And so one way, if we were being very slow and cautious and we had lots of time, all the time in the world, we might do something like the following, which is one, we verify that it's exact because we say, well, look, let's just run that process. And how do you verify? You check the partial derivatives. Say, okay, great. Now that I know it's exact, that says I know something. I know that this piece m, really what we have is that this part is partial f partial x. I say, okay, well, now I know how to find f. I integrate. And so we have our great aha. This will be our step 2, which says, look, our function is the integral of partial f partial x dx. All right, well, that seems pretty straightforward. That was almost too easy, right? Except, let's be careful here. What are we missing? We're missing something. It's an important something. We're missing the constant. And now, this is where it gets, oh, right. Okay. So, the constant is what? Well, normally we'd write plus a c for a constant. Except, we have to be careful here, because when we took this integral, we integrated with respect to x. When we're integrating with respect to x, what do we think of as constant? Y is constant. So it's no longer a constant number. It's actually anything which is constant with respect to the process that we're doing. So it's a constant function. It's some function of y. So this is not too bad. It says, look, in just one step, we've almost found all of f. Almost. Okay, so how do we figure out what that constant y is? Well, now we say, hey, we haven't used all of our information. And we say, all right, let's use all of our information. So the next step is we say, okay, take the derivative with respect to y of what we just found. Okay, so what would that be? That would be partial f partial y. Do we know anything about partial f partial y? And the answer is yes. It's here. This is our partial f partial y. And so this is equal to our, well, we'll call it n, we'll call it n partial f partial y. All right, so what does this do? Well, now this lets us solve for c prime of y. And so the last thing is great. if we have c prime of y, the final thing that gets us all the way is solve for c of y. And we're done because we put it in. All right, so that's how we can do it. Does this work? Absolutely. In practice, though, we tend to do some slightly different things. So I'm going to talk about in practice via an example. And so let's go to the example. All right. So here we go. Solve 2xy squared plus 3x squared dx plus 2x squared y plus 4y cubed dy equals 0. So let's go ahead and before we do our fast method, let's just sort of work through what we would normally do. We'd say, well, do we think this is something which might be an exact ordinary differential equation? So we say, all right, we're going to think of this as our m, and we'll think of this as our n. And now we'd run a check. And the check says, okay, take the derivative of m with respect to y. And so let's do that. So we're taking this derivative. We think of our x's as constants. So 2x is thought of as a constant for right now. Derivative of y squared would be 2y. 2y times my 2x gives 4xy. The 3x squared, well, that's a constant from our perspective, so that derivative is 0. And now we say, well, look, compare that to partial n, partial x. And what do we have? Well, now the x is our variable, all right? The derivative of 2x squared would be 4x, then times y, and then, so that would be 4xy. Derivative of 4y cubed, well, that's a constant, and so we get 0. So the whole thing is 4xy. Great. So now we know it's exact. That tells us that this first piece is partial f partial x, and that this second piece is partial f partial y. And wonderful. Now, by the way, this sort of gives you some intuition about the testing for exactness. Because what happens? If this is partial f partial x, and we take the derivative with respect to y, it says we take the derivative with respect to x and a derivative with respect to y. Here, if this is partial f partial y, and we take the derivative with respect to x, it says, well, you took the derivative with respect to x and a derivative with respect to y. And so we should get the same answer. That's the intuition. So that's why the logic behind the check works. Okay, so we know it's exact. So the next thing we would say is, okay, if we were running through our normal process, we'd say find f. We integrate the part that's the derivative with respect to x, 2xy squared plus 3x squared dx. And that would be, well, when we integrate, okay, integral of 2x, x squared. Then y squared is a constant. Derivative of 3x squared is x cubed. And then there's plus some constant function of y. So far, so good. Now, we're almost to f, except we don't know that part. Okay, so now we take partial f partial y. So we're going to take this expression, take the derivative with respect to y, treat x as a constant. So we have, okay, so that'll be x squared, constant. Derivative of y squared is 2y, so 2x squared y. Derivative of x cubed is 0. Derivative of c of y with respect to y is c prime of y. And that's going to be equal to what the partial derivative of f with respect to y is. So that's 2x squared y plus 4y cubed. And at this point we say, aha, because we like to say aha a lot because it makes us feel like we're learning. And we say, look, those cancel. So we say, look, that c prime of y is going to be equal to 4y cubed, or we can get that c of y is y to the fourth plus a constant. And at this point, we're going to choose our constant to be 0, and we'll point out y in just a second. So that tells us that our potential function, the function that we're after, it can be written in the form x squared y squared plus x cubed plus y to the fourth. Now, is that our answer? And why not? It's not our answer. The reason it's not our answer is because when we solve exact ordinary differential equations, it's a matter of find that function f of xy equals constant. All right, so I'll set this equal to some constant, and I'll just call it e. And there we go. That's our solution. And all right, wonderful. Now, could we solve for y? We actually probably could, because if you look at how y shows up, you have y squared and y squared squared, so you could think of this as a quadratic in y squared, so you could solve for y squared, and then you could take square roots. It would be a messy, messy answer, where you'd have plus or minus a square root of something where it involves more, plus or minus square roots on the inside, but it could be done. It could be done. But just because it can be done doesn't mean it should be done. In some sense, this is a better answer, certainly a more attractive answer. All right, well, see, that's not so bad. The process isn't so bad. But let's talk about how we do this, out in the mean streets of differential equations. How do we go about solving it? And in practice, this is what we do. We say, look, we're not even going to think about checking for exactness. It'll just pop out of the process whether or not it's exact. So what we have is we say, look, the part that's in front of the dx, we're going to think of that as partial f partial x, and the part that's in front of the dy, well, that's going to be partial f partial y. So we're going to say, look, f is going to be the integral of m dx, and just the real key is to remember whatever has the dx, we're thinking that as the derivative with respect to x. All right, so that's the integral of 2xy squared plus 3x squared dx, which is, carrying out that integral, x squared y squared plus x cubed plus some constant function of y. So far you're like, wow, Steve, you're just doing the same stuff. How is this different? Here's the difference. Now, instead of going through and taking the derivative of this, we're going to say, let's integrate the function n dy, which really says whatever is in front of the dy, that's what n is, that's what you integrate. All right, so now that's going to be the integral of 2x squared y plus 4y cubed dy, which is, carrying out this integral, integrating with respect to y, well, x squared is a constant, integral of 2y is y squared. So you get x squared, y squared, and plus y to the fourth, and plus some constant function which depends on x, right? Because we're integrating with respect to y, so x is what's constant. Okay, so now our great aha, how do we make sure it's exact? How do we piece our function together? And the answer is we should have the following. So the pieces which involve both x and y should match. And if they don't match, either what you have wasn't exact or mistakes were made. And so that's what you do. And so we include these into f. But we only include one representative, right? So notice here you have an x squared y squared and an x squared y squared. These match, and since they're the only pieces that involve both an x and y, since they both are the same, we have something which is exact. If they didn't match, it wouldn't be exact. Okay, so the other parts are we say, all right, now pieces only involving x are fine. There's nothing to check, and we don't compare, but we include these into f. And so we say, okay, well, there's a piece that involves only x, and that's the x cubed. Now, on a side note, you might say, well, where is it down here? And the answer is it's in that d of x. So by integrating both of these, we say, oh, we're actually figuring out what this should be here. Now, the last thing is we say, all right, pieces that only involve y. Whoops. I can't spell the word only. So only involving y. And now we also include these into f. So what's that? Well, it'll be there. And in fact, we should point out, the pieces that only involve x will show up in this integral where we integrate with respect to x. The pieces that only involve y will show up down in this integral which involve y. And again, it is showing up here. It's that constant function of y. So if we piece all of this together, we can say, aha, our function f of xy has x squared, y squared. And again, we're only taking one copy of it. We're not taking two copies of it, just one. And then we have the x cubed, and then we have the y to the fourth. And so this is our f of xy. And finally, to get our solution, we set this equal to some constant. And working our way up the alphabet, since we already used c and d, the next constant up is e. And there we go. That's it. That's the idea. And I like this method because it's sort of very intuitive. It has some built-in checks, and it doesn't feel like a lot of wasted effort. It says you integrate and just compare the solutions and piece it together, and you got what you need. It's wonderful. Now, I will say that there is something which can happen, which is it's possible to have something be exact where you can't actually integrate it nicely. In other words, there's no nice integral. So in other words, it's possible to verify that the partial derivatives match, but kind of hopeless to do the integrals. We are not going to be doing those, so don't worry about that situation. You might also be thinking to yourself, well, is it possible we're in the situation where something isn't exact, but by maybe it's doing some gentle massaging, it could become exact? And it's just, well, it's possible, but we're not going to do that either. So if it's not exact, then we just abandon this approach entirely and say, look, it's not meant for us. We'll have to look for some other idea to use. All right, so there we go. There's the ideas. So sort of like slowly build it up, or you just say, look, let me compare the two integrals and just stitch it together. Either way, you'll get the answer. Let's do one more. And just to make sure we got it down, right? The more we do, the more natural the process becomes. So here we go. Solve x plus arctangent of y plus x plus y over 1 plus y squared times y prime equals 0. Now you might be thinking to yourself, wait, this isn't of the right form. There's no dy dx floating around. Say, okay, look, we can fix that. That's no problem. We come here and say this y prime, well, that really stands for something. And what it stands for is it stands for dy over dx. And so we say, okay, we can take this piece right here and we can rewrite it. So this rewrites in the following way. Namely, x plus arctangent of y dx plus, and then this other part, x plus y over 1 plus y squared dy, and that equals 0. All right, there we go. Now we're ready to get going. And so if we're thinking of this as exact, and of course, because we're discussing exact, we should be thinking of it that way. We say, okay, so we should be thinking of this piece right here as partial f partial x, and we should be thinking of this piece as partial f partial y. And so I'm going to do it in the second way we talked about in the previous problem. Say, all right, well, so that says we're going to integrate the thing that's in front of the dx. We're going to integrate that with respect to x. And we're like, oh, this is good. We're going to integrate an arctangent. Oh, yeah. Oh, yeah. Well, so let's integrate. The integral of x is a half x squared, right? Yeah, no problem. And the integral of arctangent is well, notice the of y. So arctangent of y is a constant. So when we integrate it, it's going to be arctangent of y, which is a constant, times x. It's like if it had been 4. You integrate 4, you get 4x. In our case, you integrate arctangent of y, you get arctangent of y times x. To help notation-wise, I'll put the x in front. So x arctangent of y. And then plus, of course, some constant function of y. Okay, now we integrate what's in front of the dy term. We integrate that with respect to y. Because we're thinking, look, this should be the derivative with respect to y. So to help us, we'll break this into two pieces. X over 1 plus y squared plus y over 1 plus y squared dy. Okay, so the first piece. The x is a constant, so that's just a number. The integral of 1 over 1 plus y squared, that should be arctangent y. It's one of our basic integrals that we have memorized. And we should have expected something like this to happen. Because what should be true? If it's exact, then the pieces that involve both the variables, so in this case both x and y, they have to line up. We already had an x arctangent y, so we should have anticipated, oh yeah, we should get an x arctangent y again. Now there's the other piece, of course, and we say, okay, well, that, we have to do something slightly different. Let's do a little bit of work here. And it's not arctangent, because there's that y upstairs. But this looks like something which could probably work pretty well if we did a u substitution. So we're going to let u equal 1 plus y squared, and then du could be 2y dy. Say, well, okay, we almost have that. We're just missing the 2. All right. Boom. Now we've got the 2. But now you might be saying, but wait, we can't just put 2's wherever we want. Well, not quite, but we can if we put also halves. See, a half and 2 combine together to be 1. We can put 1's wherever we want when we're doing multiplication. So this would become integral 1/2, and then the 2y dy would become a du, and this 1 plus y squared downstairs is a 1 over u, so this becomes 1/2 natural log u, or 1/2 natural log 1 plus y squared. Okay, so that's that integral of that sort of other piece, this part right there. So we have plus 1/2 natural log 1 plus y squared, and then of course this function d of x. And now we stitch these together. Say, all right, well, we start looking at it. Say, okay, well, this piece only has x, so anything with only x definitely gets included. And as before, we'll just point out, well, it's also in the other part. It's just hiding the d of x. Okay, so we have 1/2 x squared. And then the next piece we can look at, and we say, look, x arctangent y. Well, that shows up in both pieces, and they agree. If they didn't agree, or they don't show up in one, forget it. Hopeless, not exact. We stop. But they match. So we say, great. We include that as well. So x arctangent of y. And then we come and say, oh, there's this one other part, this 1/2 log of 1 plus y squared, which is hiding up in that c of y in the other term. And only depends on y, so that gets added into our function. So plus 1/2 log of 1 plus y squared. That is our f of xy. And finally, to get our final answer to the solution is of the form f of xy equals constant. Okay, so equals constant. And we're done. That's it. You see, there's a flow here, and once you get the hang of the flow, these problems are actually not so bad. They go pretty smooth and pretty quick. So we kind of hope for things to be exact because they're good. We like to solve them. All right. Well, time for a little bit of a recap. We more or less have reached the end of first order differential equations. So what can we say about them? Well, at this point, we have sort of a couple of techniques. And so if you see a first order differential equation, what should you try to do? Well, here's a set of ideas and principles. And roughly this is a good order to go through. You check, is it separable? If it is, well, then that's something where you can solve, because we have this technique called we separate, we integrate, we uncomplicate, and things aren't so bad. So if it's separable, we have something. Okay, check, is it linear? All right, is it linear? Okay, find an integrating factor, multiply, and integrate. And so, all right, great. Is it exact? If it is, well, we just talked about that. Find the potential function. Life is great. We love it. And if it's none of those, we say, okay, is there some substitution that we can make? Or maybe some manipulation. So when we talk about a manipulation, doing some algebra, maybe throwing some trig around, something to help us rewrite it that makes it simpler to work with. And if we find something, we say, okay, let's restart running through the list. And that's it. That's what we've learned. And we're like, wow, that's pretty good. And you might at this point say, hey, I feel great. I can solve anything now. Actually, there's this word of warning down here. There's a lot of first order differential equations out there. And if you just happen to run into somebody and they hand you a first order differential equation, odds are pretty good you're not going to be able to solve it. It's hard to solve first order differential equations. The ones we've talked about here are common ways that you can make good progress. And there definitely are many, many cases in which we can make good progress. But please remember, integration is hard. If you don't believe me, just think back to Calculus 2. That's one of the big themes of Calculus 2 is integration is hard. And we spent a lot of time to learn how to handle some special cases. And so the good news is that there are some things that we can do, even in cases where we can't use any of these techniques. And we'll mention that in passing in the near future. But at least now we have a better chance. And certainly we'll have a pretty good chance of things we might see on exams or quizzes. Yeah, that's right, those things. All right, good. Well, so don't worry. We'll still see some first order differential equations, a little bit here and there. So on to our new topic, which is talking about population models. And what's this? Well, the idea is that we can use differential equations to model what's happening with populations. Now, oftentimes when we think about populations, we often think about it in terms of changing. And we can say, okay, something is going up or something is going down. So we think of, well, what can cause a population to go up? Well, it could be something like births. That's often that. Or we could talk about migration has an effect. But we often just clump that all together and say, okay, things that make populations go up, we'll call that births. Things that make populations go down, we'll call those deaths. And populations, by the way, don't just have to be things like people or animals. It can be also like, well, we're populating a tank with liquid. We're populating molecules into the air. It's just anything where there's things are going up or down. So actually, this is a very general thing. So we say, okay, what we can do is we have these rates. Now, rate is an important word here. It's not that we're capturing the number of births or the number of deaths. We're capturing the rate. So it's somehow the number of births over the whole population. That would be the rate. And so we can say, all right, what's happening? Well, P prime, how our population changes, because that's what derivatives are. They're saying, how do things change? Well, we look at the births that come in. That's what happens when you multiply the rate times P. That tells you the number of births. We subtract the deaths. That's population leaving. And so we say, oh, this is some form, the birth rate minus the death rate times P. Now, depending upon what happens with birth rate and death rate, we get slightly different things going on. And we can get all sorts of interesting things going on. So we're going to start with a really simple case, the easiest case, which says, well, suppose that our births and deaths are fixed. And in other words, when you see this word fixed, you should say, oh, that just is a fancy way of saying constant. Because, yeah, that's what we want to talk about, constant. So you always have the same proportion of things born. You always have the same proportion dying. Well, that tells us that, hey, this part right here, this K, is really just this beta minus delta. And now we're like, wow, this is great. This is one of the first differential equations we actually talked about how to solve. It's very separable, highly separable, right? Because you can think of this as dp dt. This is a constant times p, and you can move things around. So you can separate, you can integrate, life is good. And so it has a nice general solution. P equals P0 e to the kt. All right, so let's talk about a couple things that could happen. Suppose for a second that the birth rate was smaller than the death rate. Let's think about our intuition, and let's see what the model says. If the birth rate is below the death rate, that says that, a fewer number of people are being born than who are dying. Well, what should be true? If we have fewer people being born than the number of people who are dying, that says our overall population should be shrinking. We're not able to replace what's being lost. And that's actually reflected here because that says, oh, this beta minus delta, it's a negative value. And so if you think about our model here, it says, well, whatever the initial population is, you're going to have that initial population e to a negative exponent times t. So you're going to get this exponential decay. So it's going to go down. It won't get to 0, but it'll approach 0. And in a relatively short amount of time, because exponential growth and exponential decay, things happen very quick. You might even say they happen exponentially. All right. So that's one case that could happen. Let's talk about another case. Okay, suppose that the birth rate equals the death rate. What should be true? Let's think about that. It says that the number of people being born matches with the number of people who are dying. What does that tell us about our overall population? It should say that, oh, our overall population hasn't changed. Now, does that get reflected? Well, yeah, because what it really says is, oh, this beta minus delta is equal to 0, and that's our k, so you get e to the 0, which is 1, and so our population is always the same population. So it's just saying the population is stable. All right, well, of course, there's one more case we should mention, which says, suppose our birth rate is above our death rate. Well, in this case, we'll have that beta minus delta is positive. And so when we look at that, that says, hey, this value for k is positive, or we really have this exponential function where we have e to a positive number times t. Now, of course, depending upon k, it might be a very small positive number, a very large positive number, but the point is we'll have exponential growth. And so we're going to go up quite a lot. And so those are our various cases of things that can happen. Now, this is a very simple model. Of course, we can make more interesting models. And so let's talk about one more interesting model. And here we go. Suppose we have a situation where when we look at the birth rate goes down as populations grow. So why might that happen? Well, could be a variety of things. There's competition for resources, so there's not as much need not as much ability, I should say, to reproduce. Or people are like, well, I find it pretty fulfilling. I don't need more children. Maybe. But, there's a variety of things, external factors. Another way you can think of this is maybe it's not that the birth rate decreases. Maybe a similar thing could be that the death rate increases. as the population grows. In that case, it's like, oh yeah, there's more competition for resources. And so not everybody gets as much as they used to. And, or, well, okay, more likelihood for diseases or something. So either one of those leads to the same kind of scenario. So let's just focus on the birth rate one. So we say, okay, as our population gets big, birth rate gets smaller. So one way we can write that says, look, our birth rate, there's some sort of natural birth rate, but subtract something times the population. So as population gets big, the number of birth, or the birth rate, gets small. Okay, then what happens? Well, our population change is we have this birth rate minus their death rate times p. Well, you can do a little bit of rearranging. So we have some constants here we can combine together. We can pull constants out. And this takes the form of k, p, m minus p, where m and k are constants. Okay, now, we've seen this before. Do you remember? It has a name. This is called the logistic model. And this is actually a pretty important model. And if you look at it, it's also something which is separable. So we derived the solution when we talked about separable differential equations. So if you don't remember it, go back and watch that video, and you can be reminded of all the fun that we had. Spoilers, it involved doing partial fractions. It was great. And so we found the general solution. And it has the form, the population is equal to this m times p naught divided by p naught plus m minus p naught e to the minus kmt. Now there's a couple of things that we can make note of. So for example, at time 0, what's true? Well, at time 0, e to 0 is 1, so that goes away. Here, the p0 terms cancel. We're left with m downstairs, cancels with an m upstairs, which means that, yes, at time 0, it's our p naught. So it's our initial population. Okay, that's good. Now, what happens in the long run? Well, I'll just point out maybe one case, which is, let's suppose k is positive, and then we'll see what happens. If k is positive, what will happen? Well, this part will become very small because it's e to a large negative number, which means that goes away, and then the p0 terms cancel, which means in the long run we approach m. So what's the picture we should have? So our picture says, let's suppose we graph, and let's do our case here. We'll do our case where k is positive. And we'll talk about that one first. Now, one thing we can look at and say, okay, looking at this model, when do we get p prime equals 0 for a freebie, if you will? And in other words, for which choices of p do we automatically get 0? And you'll notice there's two of them. One of them is p equals 0, which really is very unsurprising. It says, hey, if you have no population, you'll continue to have no population because nothing can be born, nothing can die. The other solution would be when p equals m. And that we've already mentioned. We said, hey, if p equals m, that's what happens in the long run. So in the long run, assuming we have any population to begin with, we anticipate that p should in fact equal m. So this has an important idea. This is what's called the carrying capacity. And the idea behind that is it says, well, look, this population is in some sort of environment. And in this environment, we can handle up to a certain amount of population. And not any more, not any less. And so that's the carrying capacity of the environment. And we say, okay, well, what happens? Well, if we're below the carrying capacity, but we have some population to begin with, so in other words, we're between 0 and m, we'll see that we have a positive number, because k is positive, the population is positive, and m minus the population is positive, which means that in this region here, P prime is positive. And so our populations will go up. And it's going to approach, but it's not actually going to hit M. So it's just going to get closer to M. And you might say, exponentially close? Yes, exponentially close. That's very true. On the other hand, suppose that we're high, so we're above our carrying capacity. So we're up here. Well, K is still positive, population is still positive, but M minus population is now negative. So that says P prime is negative, which means we're going to go downhill. And so we're going to actually approach our carrying capacity. So that's the picture. So if we're below, we move up towards M. If we're above, we move down towards M. Now, one thing you might wonder is, okay, how do we get this picture? Well, it's basically because of the nature of this differential equation. We're going to talk more about this in our next session. When we understand how the P prime behaves, is it positive or negative, that indicates whether we move up or down. One thing I want to point out is that this picture looks like it's invariant under shifting left or right. And there's a very good reason for that. Can you see why? The answer is, where's the of t? There's no of t here. So it doesn't matter at what time we started measuring. So whether we started measuring our population at time 0, or if we had gone forward, measured at time 100, whatever that meant, it's still the same differential equation. So that means that there's this sort of invariance going on. So that's why we should expect that if we shifted our diagram, we should have the same picture. Okay, so that supposes that K is positive, but what would happen if K were negative? What if? Yeah, we can ask those same questions, right? And so let's take a look and see what comes out. So here is the K negative. Now, as before, we can ask, well, when does this equal 0? And we still have the same answers. So we say, okay, well, there's these interesting cases, namely when the population equals 0 or when the population equals M. And I'm not going to call this carrying capacity because I want to look at the diagram before I call it anything. And now we say, okay, well, what's happening? Suppose I'm in that range. Well, in this range, K is negative, P is positive, M minus P is positive. So the net effect says, oh, P prime is negative. Which means what? Means that we're going down. So we're actually going to be going somewhat opposite from where we were before. So we're going to be doing something like that. And you say, okay, what happens above M? Well, okay, negative, positive, negative. Their signs combine say that P prime in this range will be positive. And so we're actually going to be moving up. And this one, actually, not so obvious, but it's not going to slowly go up over time. It's actually going to blow up pretty quickly. And if you're wondering, wait, what? How? It turns out that in a short amount of time, you'll get a 0 downstairs. So you can work it out. It's best seen when you work with actual numbers instead of symbolic ones. But the important thing is we see that, hey, things are moving up. And looking at this, you say, oh, there's sort of something interesting going on here, where we have these interesting solutions, which are just constant solutions. And over here, we have the case where I'm heading towards that. So if I'm just below it or just above it, it's like, oh, we're heading towards that value of M. On the other hand, here's a constant solution which says, oh, we move away from that. So if I'm just above or below, it's like, well, go far away. And so this sort of says, oh, there's two interesting behaviors going on. Do we have names for them, and can we classify them? And we will in our next session, which means you should come back because it's going to be good times the next time we get together. Thank you for coming today. Hope to see you again. Bye.